to take care of us, to take us to the lunch, and enjoy the city. He promised many things for today. I don't know, where is him? Oh, he's already here. All right. Up to now, we have heard many things about theories, models, predictions. It's time to wake up to the real world, experiments. I would say it's much easier. If you cannot explain, it's not your problem. You just measure. You have to find partners who work in theoretical institutes to give you explanations. So today I will try to introduce and present the Hexbugs. It seems they are quite famous. Everyone is interested in how to discover his particularities and how you can use it in your lab. It's a toy, first of all. It was developed as a cat toy, to be more specific. And we try to understand this right. This is me, this is where I work, and my team has 4 colleagues, all professors, and students, undergrad students, master students, postdoc students, not students anymore, it's a regular colleague. And the next year we start with our PhD program. Just a few words about the city where I live. Recife is in the northeast of Brazil, as you can see. Okay. That's Recife, this city. It's more or less halfway to this one. So the organization invites people from both sides. That's the advertisement of the city. You are welcome to join the city. The temperature never changes. It's around 24 to 30 at most. That's real pictures. Carnival. Beer. Carnival again. That's the university. That's the rural, this name, because it is specialized in agronomy, veterinary, in earth, and a few other things connected with nature. It's a very beautiful campus. It's very green. That's our university, the main building, and the physics department is over here. That's the local picture. It's quite new, I would say. We have 15 years old, and more or less 25 professors. That's few information. Let's start the ride. Hexbugs is a product of a company created as a junior company that included from university. They have few designed products. The bug that we are used to use, and I will going to speak, but they also have few others. They have somehow a very sophisticated way to move, and the noise associated with those toys are completely different. If you feel that this is already complicated, never look to the others, because it's so strange. You look, it's but it's possible. Just try it. How much does it cost? Almost nothing. Even in Brazil, you can buy 5 for this price. As you can see, it's in Brazilian reais. It takes 2 days to get you home. So you just buy it right now, and to the end of the conference, you have it. But you can order directly from US where it's made. That's half the price. Or if you buy, I don't know, 100, the price can be much cheaper. So that's where you start. I just need to define few variables. The basic variables, everybody already know here. All the lecturers spoke those variables. The position, the polar angle, the orientation, and the velocity. That's exactly what I need to explain. That's an example of this system that's on the table. Please just come here, it will be here. The potential with few Hexbugs is not the same because we need the contrast. We need the bug to be black to help the data acquisition. The blue arrow is the polarization, and the green one is the velocity. As you can see, it plays. It's quite nice to see the work done. You can observe a few things about these trajectories. First of all, the velocity changed very much. There is a noise associated with the velocity. I'm sorry. And the polarization, orientation, is very smooth. So keep in mind that information, because there exists two relaxation times. One is connected with this smooth behavior, and another one connected with this velocity that changed so quickly. Look to details of the Hexbug. You need a lab to make these images. The Hexbug has one vibration motor, vibration engine, that's it, you can see. It spins at 130 hertz, you can see here. To make those images, those recording, you have to go up to this frequency. And we also use 10 bits. Regular device just recording 8 bits, not 10 bits. Regular pictures, JPEG images are 8 bits. So if you have a 10 bits, you cannot see it on your screen. Your screen is 8 bits. You need to look at the numbers, not the picture. You cannot see it anymore. So you have some technical issues when you go away from the standard formats of image. How do you know the frequency? You just ask for one of your students to count the number of spins. You find the number. All right. How does this bug move? To answer this question, we just need 3 cameras, one in top, side, and front view. Put the camera and record the movement. If the movement is smooth, you can use the equations everybody here knows. One associated with the velocity, another one associated with the angle of the orientation. And that's it. It's a 2D problem. But just remember, the topological surface isn't plane. It doesn't help. When you see this image, that's a front view. You can see the student's hands getting away. The time is passing 40 times slower. So 1 second here, 40 seconds here means 1 second in reality. It spins, the engine, it jumps, it doesn't walk. So the movement isn't continuous, it's a discrete movement. And also, it goes up and goes down. We heard in the previous talk, the seminar, that, I'm sorry, it wasn't the previous, one of the lectures, active matter doesn't like 3D, but this bug does not like 2D. It's trying to get into the third dimension. That means gravity may be an ingredient that is missing in the description of this bug. Nobody includes the gravity in the equation. So if you look at the side view, the best recording of the tree is this one. You can see the jumps. It never goes back, only forward. In the end, it flies. That's the kind of movement. It just unglues from the surface, go upward, and go down again. In the top view, you can see the legs showing up in the left side, in the right side. It means the bug is making a kind of torque. All right, that's the movies in slow motion for the bugs. Once you know the bugs, we have some idea how it works. The first information we need is to know about the noise. So what we do, we measure the noise. We just put the bug in a plane. It's a glass, you can see here, and it's a circular wall. You let the bug walk freely for a very long time. I don't know, 15 minutes. It's quite a long time for the Hexbug. We just establish a circle to remove all the data above the circle because we don't want interference with the walls, the boundary conditions. And then we make a histogram of the fluctuation, position fluctuation. Essentially, it's the velocity. You just remove the time interval. You get the numbers. The average position, average fluctuation is around 0. It's in centimeters. And the mean square, the variance is a finite number. So you know experimentally the noise of the Hexbug, and it doesn't change. You can buy the bugs if the battery is the same, the model is the same, the noise should be the same. Of course, can be some damaged equipment, if I call it equipment. But that's it. It comes for free for you. You have a device that produces a fixed noise, fixed frequency, and you can use it in different scenarios. For example, when you introduce potentials that introduce force, in principle, the noise doesn't change. So you have one of the most difficult terms in the equations solved. You already know the noise. That's the histogram, you can see. I'm sorry, this is the correlation. The correlation should be a delta function. But if you look to the time scale of the delay between the noise and the noise plus a delay, that's what we get. It's very fast, it goes to 0. That means a classical Gaussian noise. But if you look at longer times, it's not the same. You can see I go up to 10 minutes. You have a maximum at 0, but there are some permanent offset that does not go to 0. I don't have a good explanation, but this is what the correlation function shows for longer times. If you just look here, around the 0, this is the equation. This is the histogram. I'm sorry?
It might depend on the velocity, since the battery is, after 10 minutes, is maybe decreasing, and then the self-propelled velocity is also decreasing.
Yes, it would be a good answer, but we take care very carefully about battery. Every experiment uses a brand new battery. You put a new battery, put on the potential. If you take it out, the battery cannot be used anymore. And we measure the electrical potential in the battery before the experiment and after the experiment. We guarantee the same level of conditions to all the experiments. No, after 10 minutes, if the level of the battery is down, we just discard the experiment and we do again. We guarantee the experiment was made with the same level of battery.
And I guess for measuring the noise correlation, you don't use the boundary, right?
Yes.
It's a free bug. Okay. And it's not like a 1/f noise or something special. I don't know. Like, there's no structure, I guess, in apart from those oscillations, the decay of the noise with.
As I said, I have no explanation for those oscillations.
Okay.
I would include the whole data, especially because most of the data is above the circle, where the speed of the Hexbug is slower, because it collides with the wall. So it loses velocity. So most of the points are there, but I just give them away. All right. Here, that's too much. Sorry. That's the Zoom issues. All right, here. This kind of graph was shown every day in every lecture, the mean square displacement. For me, it was a surprise. I wasn't expecting to see it in all the lectures. Especially this one. That's the mean square displacement for the angle. It wasn't for the position or the radius. And that was I took the picture of the board, the blackboard. And you can see when you include the noise, translational noise and angular noise, that was the difference. That was measured. Of course, I have the others, but not ready to the presentation. It needed more time to do that. All right. This is something special that appears when you include special potentials. We have a characteristic time that's associated with the self-alignment. I cannot control this time. This time is a consequence of the contact of the Hexbug and the surface. Some surface will have different relaxation times. If you just polish the surface, you may change this number, but I have no control. There are other two times associated. One is the thermal time. You just let the system just find the equilibrium on your system. And the third one, it depends on one parameter.
Antonio,
I'm sorry.
one moment. The self-alignment time, tau, is it just associated with the velocity aligning with the polarization?
Yes.
Okay, thank you.
There is this one is connected with the random movement, and this one, that's the climbing time. Since I have some gradient in your geometry, it introduces energy and remove energy when you go up and down. And there are some time associated. So you have 3 times, and we measure those times. There are a few tricky ways to do that. The most difficult is the relaxation time associated with the self-alignment. This is pretty hard. This is the graph where we get this relaxation time associated with the self-alignment. You need to measure the angle between the velocity and the orientation, and how long, how much time it does to realign. So you have the points, the green one and the red one. That means when the misalignment is the most, and the red one is most aligned.
There is a question from the Zoom chat. Someone's asking, how do you measure the self-alignment time? I think that's what you are explaining.
Yes,
right?
yes, that's what I'm explaining. You have to measure this angle, the misalignment, and if you plot against time, you have a time series of the misalignment. This characteristic time comes from the time requested to go from the blue to the red. But it's not a linear time. You have to make some approximation. For example, exponential decay from the top to the bottom. So you introduce one parameter and you extract this information from the data. You have a time series very long. Look, it's 30 seconds. I go to 10 minutes. So you have, to every pair of blue and red, you have one number associated with the exponent of the decay. So you have a time series for the characteristic time. You just do your work as experimental, and you find this number with the precision.
Just a quick question, what's the frame rate?
For this experiment is 30 frames per second. But of course, you can go much higher, but there is no need.
Yeah. Can you go back to the previous slide? So the time for the self-alignment, it depends a lot on the eccentricity of your
Yes.
parabolic domain. So what does it mean? That when you are like in a circular symmetry, the self-align is almost, is more close to zero and then it's going farther. Can you like explain that?
If I would give this explanation theoretically, it would take me much long. But as experimental physicist, it's very easy. The Hexbug likes surf. It goes surfing. It just go up in the wave and go down, falling as a surfer.
So it's
When it does, it's explained why the misalignment goes up so fast. It just go up and fall to the side.
So it's an externally forced alignment, right? The alignment is occurring because of the external force.
Yes, somehow. Yes, there's a surface, it's fixed, it's topological somehow. Naturally, you need an acquisition time faster than those characteristic time. Otherwise, you don't see it. All right. Oh. That's the basic equations you can use. You also, everyone here saw many times those equations. Naturally, you can add more terms here, or tensor if you prefer, make it more complicated. But once you have any model, we can measure the parameters. Up to this slide, I didn't show any equation, so I'm just showing experimental details. If you suppose the movement of the Hexbug obeys this equation, I can give you the value of the beta, of the D, and me. Just plain numbers, you can find it. I have, I don't know, as many experiments as you desire, because it's simple, cheap, and fast. Of course, it takes some cloud space, but it's simple. This is a very famous experiment made by Olivier Duchot and Vincent Demery. They used one antenna. It was a kind of, oh, that equipment is old. Nobody's using. Let's take it. Let's see what it happens. They took this antenna from cable TV that stays somewhere in your storage room. They put a Hexbug, they measure as I did, and they found two solutions, the orbiting solution and the climbing solution. They just wrote nice words and they published a PRL. That's what they did. And they used that equation that I just showed before. That's the picture of the Hexbug. That's exactly the same model, I guess, and few trajectories that they included. Naturally, we reproduce this experiment. Sorry, that's the zoom issue that is delaying the picture. I already clicked to the next.
A quick question while it's going there. I assume there's no problem with having many particles insofar as tracking them. It's okay to have many particles, and you can keep tracking each one individually without much problem.
Yes, our acquisition capacity is enough for, I don't know, I would say dozens.
And also a curiosity, can you put armors of funny shapes in the Hexbugs and make them interact in some funny way?
Yes. There are papers that they do active matter. They make special networks. Inside every network, every cell, you put a Hexbug. And depends on your network, you have a shaker inside every cell, so you have a network, active network. That's the name. Look, Hexbug, it's a toy box. You can use it. It's to be used. Simple, cheap. What matters is the idea. It's not the equipment. You're not better than anyone because everybody can buy it. I'm not talking about the Hubble image. I'm talking about something that costs $5. That's it. Have a good idea, you can publish. That's the point. All right, that's the same experiment, but now made with a 3D printed potential with our little bug. On my screen, it's perfect. Here it is disappearing. All right, let's just jump to the next. Why to make parabolic potentials with anisotropy? It was a work published 2 years ago by the group of Clécio Souza, my colleague of Recife. It's from another university. It's very similar. My university has a rural in the middle. This one doesn't. They did the simulations, and they found if you confine the bug, the Hexbug, in a parabolic potential with anisotropy, and this parameter is the anisotropy, essentially is the it's a control parameter. It's not exactly the same. If you change it, you find different solutions for the equations. For example, in two shows in Vincent Demery work, they found only 2 solutions, the climbing and the orbiting. If you change this parameter, introducing anisotropy, you find different scenarios, different solutions, and those solutions are separated by a dashed line. That means it's not a transition, it's fluid. You can go to one side or to the other side. But eventually, you find one that is different. It's a solid line. Something changed when you cross a solid line. In this work, they calculated the topological charge. That means the trajectory carries some information of the system, and you cannot cross the line. If you have one state in this region, you carry a topological charge, and topological charge have some symmetry properties. It means it's stable. It's quite stable. And to see experimentally those charges are one of the tasks to this work. That's why we printed, I don't know, many. My students know more than me how many 3D printed potentials we have used. But that's one of the works here, to change the eccentricity of the system here and to walk through the phase diagram and to find those transitions. You make the potential a little bit behind the line and a little bit above the line. And you can see different states. It's quite similar, but you cannot cross the line. This is the impressive. When you design a very simple experiment, and they show that physics is it. It's at your hands. You just need to know it.
How do you change the beta parameter experimentally? Because I think it's fixed for the Hexbugs, isn't it?
Yes. Beta cannot be changed. Beta is the parameter in front of the self-alignment force. That parameter cannot be changed. Actually, it can, but you cannot control it. As I did, if you polish the surface, you change beta. But I don't know if it becomes bigger or smaller. It survives with time or not. It's better not to change. Let it as it is. You can change the eccentricity of the system. Of course, you can put a weight in the Hexbug. It increases the total weight. It obviously will change the connection with the surface, and you may have what you are looking for. All right. Since we can print anything, you can think how to make perturbation of the trajectories. You can introduce topological perturbations. You can introduce noise on the surface. You can make defects, like as you have seen in the previous talk, and see what happens with the Hexbug. It's free. The two things that really impressive, 3D printer, have to be used for good, not for playing. What? All right. This is the special potentials where we are looking for the symmetry break. We made in a different way. And we can try to understand the stability of the system. I'll just pass faster because it's time for someone else. All right. Our lab also does many other things. That's one of the research lines that Hexbug to be printed potentials in other things. Something else that we are doing is the dynamical systems. We studied chaos. We designed some robots to be printed in Arduino mounted and coded. We do in these lemon billiards. They are quite big, by the way, like 2 meters long. And the robot just play this strike in straight lines inside the system. You just track the position. You can construct the the Poincaré phase diagram. And you can find chaos, stability in other systems. That's kind of things you can see. Also fish, it's another kind of active particle that we are getting experience. Those little fish move, you can record all of them. That's one example of capacity to identify in real time fish moving, swimming, with no identity change or occlusion in both sides. It isn't animation, it's a real experiment. We just color the fish to identify them. This is also another experiment with larvas of zebrafish. You put one larva in every one of the wells, and you can analyze the pattern with time. That's the last slide. You should pay attention carefully because they move and stop. They move and stop. You can do all the statistics at once, because there are 48 different active particles, if I can call particles, and they do not interact. They are blind at this stage of development. So that's, all the information you can get. That's one example of what experimental lab in active matter can do. We produce a lot of data, a lot of experiments. They are quite fast experiments. We produce data. And after that, we need friends, many friends, like the whole auditorium. I'm not the owner of the data. The data belongs to science. If someone wants the data, I'm here to share it. And that's it. Thank you.
Thank you very much, Romaguera. So questions?
Thank you for the lecture, Antonio. Very, very nice. I have a simple question, actually. Maybe one philosophical question. Did you set up the Hexbugs to obey this kind of self-alignment? Because your alignment, I think, depend on the velocity intensity, I think, the first term in the angular equation, or this emerge naturally?
First of all, the model you use, it's your choice. Not exactly you, but it's anyone's choice. I just measure. There exists some restoring force that makes the angle between orientation and velocity be the same. I don't know the expression. Everyone in the current scenario, current academic understanding is to use this torque, the torque between the angle, the orientation, and the velocity. So in the end, it depends on the velocity. But you can?
Naturally.
But not necessarily.
Ah, sure. Because there are a lot of the kind of alignment terms which doesn't depend on the velocity strength, for example.
This is the time series of the misalignment angle. It's non-trivial.
Yeah, I see.
There's a lot of variability between Hexbug and Hexbug. So
I'm sorry?
There's a lot of variability between Hexbugs. So some of
They're
them
essentially the same.
So they don't have
To be the truth, I bought 50 Hexbugs. I had to test all of them. They are not able to be used to experiments, all of them, because they have some defects. For example, the legs are shorter. They don't walk in straight lines. They like to stay spinning. So you just remove those problems. You get 5.
Yeah, so that was my question, because the motor rotates in one direction, so that means that it has an inherent chirality, all of them.
If they start rotating in one direction, eventually they stop this state, they can go to the opposite direction. They do. Because there is no reason to stay in the same state. There is a noise, a pretty big noise.
But that was the circular stadium, right? That's why it was
even
circular,
the circular,
because of the wall, not because of the...
If it is plain,
But if you measure how likely it is for the Hexbug to rotate clockwise or counterclockwise, I'm sure you're going to have a preference.
we did that.
Okay, and you
And
did.
the number of turns in every direction tends to be 0. If you wait enough, it tends to be 0.
Okay. Wow.
It goes to one side.
And the last one, the legs get shorter and shorter with time. because
Yes.
they're walking. So how long does one Hexbug last? So for how long can you make experiments with one good Hexbug? How much does it cost
How much does it cost?
to run experiments for one paper, for example?
It includes my lab. Well, if you want to start now, as I heard, you are a new professor. You are setting up your lab. You can start with a mobile, used one, by the way. Doesn't need to be brand new. A few Hexbugs and a dream. It can be done. Our first paper, just to finish this story, first paper about active matter was made almost in this way. I used mobile, a robot that was made with almost nothing in a lot of time. That's the way we did. And it was a scientific report. So, believe.
Antonio, I have a question. Let's think about the eccentricity 0 for the parabolic domain. Is this orbiting state or the one pointing out depending on the distance of the Hexbugs moving from the center of the parabolic domain? Like, if you look at the videos, you can see that the orbiting state, when it's moving like in circular motion, it's closer to the center of the parabolic domain. And for me, from what I have seen in the experiments, it seems that when the Hexbug is trying to go outside the parabolic domain, it's doing this other state, like trying to pointing out. So it depends on the distance?
Yes, it depends. There are three characteristic times. One is the time to go up, the climbing time. Okay. The second one is the self-alignment time, as we already mentioned. But there is a third one that rules the behavior of the Hexbug when they are near the center. If your system is too big, it loses the correlation between the climbing time and the central movement. It becomes random. If it's random, you cannot go up. If you make your system too small, it will never reach this, if I can say equilibrium, but it's the random movement in the flat surface. If you make it very big, the flat surface, it's the majority area of your system. So this time dominates the behavior of the Hexbug. If you make it too small, the climbing time will dominate. You have to take care of these three times.
Yeah, okay, thank you.
Okay,
so David has
okay,
another.
please, this is the last question because in the interest of time.
Hi, it's a really nice work. I don't know if you have already measured it, but do you know if the zebra fish or even the zebra larvae respect the same model of the Hexbugs? For instance, the self-alignment or something like that?
Zebrafish is far more complicated than Hexbug. For example, your question, zebrafish has more degrees of freedom than the Hexbug. And the self-alignment, it's a question I even don't know how to define properly the orientation of the zebrafish. I should consider where it's looking at or the tail to the head, because it can move like a human, can do anything. So it's more difficult. It belongs to the area of computer vision. You don't define an arrow, a vector. It's a field. It's not a vector.
I see. Thank you.
I have many questions, but in the interest of time, let's think again.